Today's lesson is about the composition of trig functions and inverse trig functions. The big idea is that something like cosine inverse of cosine of x is equal to x sometimes, but not always. So we have to come up with a way to understand when it's true and when it's not true. Quickly, I'd like to rewind and think about some other functions that aren't trig functions and how they interact with their inverses. So let's take a look at f of x equals x squared and g of x equals the square root of x. And the question that we're really asking is, what is f of g of x? Is it equal to the identity? What is it equal to? Just plain old x or what? So we'll plug g of x into f of x, and you see you get this function square root of x squared. So what we're doing is we're thinking about what that would simplify to for different values of x. So I'll start by thinking about the domain of the inner function, g, and of course the domain of the square root is x must be greater than or equal to 0. Meanwhile, the range of the outer function f is also x must be greater than or equal to 0, and what that means is the graph, or the result of this composition, f of g of x, is only a portion of the line y equals x, and it's the portion of the line in quadrant 1. So what does that mean then? What if we take the composition in the other direction? What if instead of looking at f of g of x, what if we look at g of f of x? Of course, as you know, function composition is one of those things, kind of like matrix multiplication, that is not commutative. So g of f of x will not necessarily be exactly the same as f of g of x. In fact, they could be very different. But in this case, we're looking at the square root of x squared. So let's again take a look at the domain of the inside function, which is now f. Of course, x squared has a domain of all real numbers, and the domain of the outer function, or I'm sorry, the range of the outer function, g, which again is defined from 0 to infinity. So this creates an interesting result. If x is a positive number, I square it and square root it, and I'm back where I started. However, if x is a negative number, when I square it, it becomes positive, and when I square root it, it's still positive. And what that means is the square root of x squared is exactly the same as the absolute value of x. Okay, let's look at a couple other functions, still not trig functions, kind of building up to that. What if f of x is the natural log of x and g of x is e to the x? Once again, these are inverse functions, so you would expect when they are composed that they will undo each other. So let's take a look at that composition. And we'll look at it in both directions. We'll ask what is f of g of x, and we will also ask what is g of f of x. And I guess I should just point out that if you just take two arbitrary functions, f and g, and compose them, there's no reason to expect that they're going to be the same thing if you compose in opposite directions. Function composition is not commutative. Okay, so for f of g, the domain is all real numbers, and the range is all real numbers. So that gives us a nice result. F of g of x is exactly equal to y equals x for all values of x. If you plug in a negative, it works. Plug in a positive, it works for 0. Meanwhile, g of f of x, this is now the natural logs on the inside, and the natural log only takes positive inputs, and the exponential only gives positive outputs. So now our graph is just the quadrant 1, excluding the origin. Okay, now we're ready to look at cosine of cosine inverse of x and sine of sine inverse of x. What will these compositions give us? So let's look at the domain of the inside function. Domain of sine inverse and cosine inverse is the same. In both cases, it's negative 1 to 1, inclusive. What about the range of the outside functions? So the range of sine and cosine is the same. Again, negative 1 to 1. That means the composition is going to yield this little tiny portion of y equals x, just on the interval from negative 1 to 1. So, for example, if you wanted to work out sine of sine inverse of 0.75, the answer would be obvious, 0.75. And if instead you wanted to work out something like sine of sine inverse of, well, how about 1.3? Well, 1.3 is greater than 1, so that is not going to be defined. And that's basically how the composition of cosine and cosine inverse and sine inverse works. Now, tan of tan inverse of x is actually a different story. It's equal to x always, for all values of x. So just kind of like we did with e of natural log of x. And that's because the domain of tan inverse is all real numbers, and the range of tangent is all real numbers. So no matter which ratio you give it, tan inverse will find an angle, and tan will take that angle and tell you the ratio right back out. Okay, well, I think we're finally ready to talk about that Charlie Brown problem about cosine inverse of cosine x, which of course is different than cosine of cosine inverse. Now the domain of the inside is cosine, it's all real numbers. And, well, the range of the outside, remember cosine inverse, its range is defined only on that top half of the unit circle from 0 to pi. So what that means is if you plug in an input from 0 to pi, the answer is going to be quite obvious. Cosine inverse of cosine of anything from 0 to pi will just be that angle that you plugged in. When things start to get a little bit tricky is when we pick an output, say like 3 pi over 2, that's larger than pi. In a case like that, cosine inverse of cosine of 3 pi over 2 will not give us 3 pi over 2. Instead, you think of cosine of 3 pi over 2, we know that's 0, and cosine inverse of 0 will be pi over 2. So what that means is it's sort of thrown across the unit circle to an angle on the interval from 0 to pi with the same x-coordinate as 3 pi over 2. And graphically, what that means is we start to get this like little sawtooth Charlie Brown like shirt design here, where the angle starts to decrease, and it keeps repeating every half turn on the unit circle. Increases 0 to pi, decreases pi to pi over 2, increases 2 pi to 3 pi, and so on. And it just keeps repeating in that same manner, exactly like you see on Charlie Brown's shirt. If we took a look at now maybe sine inverse of sine of x, you'll see a very similar story. Not exactly the same, but very, very similar. This time the domain of our inner function, sine, all real numbers, its range, sine inverse, its range is defined on the right half of the unit circle. That is the interval from negative pi over 2 to pi over 2. And that means if you plug an input on that interval, negative pi over 2 to pi over 2, into sine inverse of sine of x, you'll get quite an obvious output, exactly what you plug back in, because sine will find the ratio, sine inverse will find the angle. Meanwhile, if you plug in something that is maybe larger, let's say, how about sine inverse of sine of 3 pi over 4? This is something that is now in quadrant 2. Well, what will end up happening is it'll find an equivalent y-coordinate in quadrant 1 because the sign is also positive there. We're thinking instead at the angle pi over 4. That's what will output again. And again, graphically, sine inverse of sine will start making that sawtooth-like shape that you're seeing on Charlie Brown's shirt. Okay. Lastly, what about tan inverse of tan of x? This is, I think, the most interesting, the strangest one to try to understand. In this case, the domain of the inside function is not all real numbers. There are some things you can't plug in at all because it's tangent, and tangent doesn't like all the odd multiples of pi over 2. So I couldn't plug in pi over 2. I couldn't plug in 3 pi over 2. Meanwhile, the range of the outside function is actually, it says all real numbers there. It's actually limited from negative pi over 2 to pi over 2, not inclusive. Sorry, I got a little mistake on there. And what that means is if you plug in anything from negative pi over 2 to pi over 2, it'll output exactly like sine does. In fact, that piece looks exactly like sine inverse of sine of x does. On the other hand, Tan is always an increasing function, so it doesn't come back down like you see in Charlie Brown's shirt. Instead, you see all these like y equals x like lines on every odd interval from negative pi over 2 to pi over 2. Okay, I'll wrap this video up with a quick summary of the domains and ranges where the trig functions, when composed with their inverses, are equal to x, the identity. And then in our next video, I'll talk about a few examples where they're not equal to it, so you can get a hang of how to work those out. I guess the first thing to know is that if the inverse is on the inside, then for sine and cosine, sine of sine inverse and cosine of cosine inverse will be equal to x anytime that x is in the interval negative 1 to 1. Meanwhile, for tan, it's always true. Tan of tan inverse of x is always equal to x because the domain of inverse tan and the range of tangent are both all real numbers. Meanwhile, things get a little tricky if you're going to do the regular trig function on the inside and the sine inverse on the outside. The only time that sine inverse of sine of x is equal to x is when it's on that right half of the unit circle, negative pi over 2 to pi over 2. Same thing's true for tangent. Meanwhile, for cosine, cosine inverse of cosine of x is equal to x when x is in the interval from 0 to pi. The next video will talk about a few examples of what to do when the x's are not in those intervals, specifically in the latter cases, because those you need to do a little bit of extra work. We'll also see a few examples of what to do when sine is composed with cosine inverse, or cosine is composed with sine inverse, and so on and so forth. Thanks.